Hello everyone, welcome to the Exam Prep 13 video walkthrough. I'm Carlo and today's walkthrough is all about graphs. Hello graphs. So there's a lot of topics covered in the worksheet, so I'm going to go ahead and review those. Feel free to skip around to parts that you want to focus on more than others. So let's backtrack and real quick talk about what graphs are. So really they're a generalization of concepts that we've already covered in the course. Going back to the first few weeks of the course where we talked about linked lists, these were just a set of nodes connected in a sequence. Well, then we expanded upon linked lists to make trees in which we relaxed the constraint that a node could have only one child, right? So a linked list is a tree, and then trees are just a generalization of linked lists. You can have multiple children. And then graphs are a further generalization of trees that we've been working with to the point where now we can have cycles. Okay, so let's just go over some basics so we're all on the same page with graphs. We have a set of vertices. These can have a value or a label, just like with trees, just like with linked lists. And these vertices are connected with edges, right? And these edges can also have a label or a value. So we have the concept of directed versus undirected edges. So in this visual, these edges are undirected because we can move in either direction. So it means we can go from A to C or from C to A. Now contrast that with directed edges. In this case, we specify an arrow that indicates the specific direction we can go. So it means we can only go from C to A and we can't go from A to C. Unless, of course, we have arrows in both directions. So you can think an undirected edge, in fact, is just a directed edge with arrows going in both directions. Okay. Oh, yeah, like this. And then we have cyclic versus acyclic graphs. So a cyclic graph just is a graph that can contain paths, can contain cycles. And cycles are paths without repeating edges that start and end at the same node. So this graph right now has no cycles. If we add this edge, now it has a cycle because we can get to A, back to A using this path A, B, C, A, and it doesn't repeat any edges. But if we change this edge like so, it's directed, but it's now not cyclic because there's no path that brings us back to where we started. And this type of graph actually has a special term called directed acyclic graphs because it's 1, directed, 2, it's acyclic, 3, it's a graph, and we call that DAG for short. So frequently in problems, we'll say, assume the graph is a DAG, for example. Here are some common terms that I'm not going to sit here and read to you, but it's just a good reference point in case you're not, to make sure that your understanding of terms like adjacent or neighbor matches what we're actually talking about. So feel free to skim through this if you wish. Okay, so far we've talked about graphs from a theoretical viewpoint, how we visualize them, but how would we actually code a graph representation? Well, there's many ways to code a graph data structure. All you have to do is satisfy basically the API we've defined here. If it satisfies these properties such that we have nodes, we have edges, we have a concept of directed edges, then we're good. There's many ways you could code a graph. But here's some common representations. One is an edgeless representation. So with this approach, we have an object for every node in our graph. And each object has a mapping to its list of incoming and outgoing nodes. So if you look at this example here, the node A has 2 outgoing edges. A goes to B and A also goes to C. So here, and then it has no incoming edges. So here for the node A, we're pointing to a list of outgoing nodes. So that'd be 2 and 3. If you represent A as 1, B as 2, C as 3, and then incoming edges is an empty list. For node B, it has one outgoing node. That'd be pointing to 3, and then one incoming node coming from A, etc., etc. Okay, and then like an even simpler approach is just an edge set. So we have a set of edges in our graph, and you just store all of these edges in a big set. So this is probably like the easiest thing to do. There's no big data. In fact, you probably don't even need to have a separate data structure. However, you might immediately be seeing some problems with this. Like any graph operation is going to take linear time with respect to the number of edges because you're going to have to iterate through all the edges in your set. For example, if I need to find the neighbors of a node, I'd have to go through all of the edges and see if any of those could be neighbors because there's no way to know without looking at everything. Okay, so the next two representations I'm going to talk about, which is adjacency matrix and adjacency list, these are the more common representations that you'll actually see in practice. So the adjacency matrix approach is we store a V by V matrix, where V is the number of nodes in our graph or a number of vertices, and each spot in the matrix represents an edge. So in that spot, you'll put a 1 if an edge exists, or 0 if it does not exist. So let's look at this example here. We have 5 nodes, so I have a 5 by 5 matrix, and every spot represents an edge. So if I go 2, 3, that represents an edge going from 2 to 3, and there's a 1 there because yes, there's an edge from 2 to 3. What about 1 to 2? So here I go 1, 2, there's also a 1. But if I look 2 to 1, there is no edge. So if I go 2, 1, then there's a 0, right? So basically just fill out the matrix based off the edges in your graph. So this takes V squared space, right? It's a V by V matrix. And if you want to find all the neighbors of a vertex, you just go to that vertex and literally iterate through that row. So that would, and keep track of all the squares that have a 1 in that value. So that would take linear time with respect to the number of nodes in the graph. So this is a handy way to remember that the maximum number of edges in a graph is V squared, right? Because we have V vertices, and we're creating a V by V matrix that is supposed to encapsulate all our edges. So if we had a fully connected graph, then we'd have exactly V squared edges, right? Another handy thing this helps to keep in mind is that an undirected graph would have a symmetric adjacency matrix. So if all these lines were undirected, then an edge from 1 to 2 also means we have an edge from 2 to 1. So if we have a 1 anywhere, then we'd also need a 1 sort of on the symmetric opposite side. Like an edge from 1 to 2, a 1 there would also need an edge from 2 to 1, so we would also need a 1 here, etc. Okay, let's talk about adjacency lists. So this is a representation in which we keep track of a list in which each position represents a vertex, and each position in the list points to a list of its neighbors. So, for example, we have node 0 pointing to a list containing 1 and 2. That means we have vertex 0, and that points to nodes 1 and nodes 2. Then vertex 1 points to node 3, vertex 2, etc., etc. You get the idea. So this is nice because it takes a lot less space potentially than the adjacency matrix. We just need V space for all the vertices, and then space proportional to the number of edges in our graph, right? You add an element to one of these lists if the edge exists. If an edge does not exist, we're not going to put any value there. So contrast that with an adjacency matrix where we put like a 0. And then it's like, this depends slightly on how you think about it, like exactly what operation you need to do. But if you just needed to return a list of all the neighbors of a vertex, You could do that in constant time because you just return the list that the vertex's position is pointing to. Okay, so that's it for just what graphs are. Now we're going to be moving into graph traversals, aka DFS and BFS. Okay, so let's start with DFS. Now the goal with depth first search is to explore a graph in which we visit all of its nodes. So one thing we need to keep in mind is graphs can have cycles, right? That's what differentiates them from a tree. So we need to keep track of the nodes we've been visiting in order to avoid infinite loops or recursion. If you just continue visiting a node's children, then you can get stuck in a loop. So the idea with DFS in particular is we traverse as deep as possible into the graph as we can, and then once we get stuck, we backtrack. So this is the pseudocode for the recursive approach for DFS. You start with this DFS procedure, and you just set visited for all nodes in the graph to false, right? Because you haven't visited any of the nodes yet. And then you go through all your nodes in your graph, and if you haven't visited that node yet, you call explore on that node or visit. And the explorer function, well, what it does is it first sets visited of the node you're exploring to true. Makes sense. And then for every edge going from V to U, so basically all the neighbors of our vertex V we're exploring, if you haven't already visited that neighbor, then you recursively call explore on that neighbor. Okay, so this is exactly what we've outlined here as the idea with DFS. We're going as deep as possible into the graph because once you explore a child, then you immediately call recursively explore on that child, etc., etc. Eventually, you'll hit the base case, which is there are no children that you haven't visited, so then you don't recursively call explore. And in that case, then you go back up to the parent and see if there's any more children that you have left unexplored, etc., etc. Okay, so, oh yes, before an example, if you want to do your pre-visit or post-visit operations, this matches very similarly to how we talked about DFS with trees. If you process a vertex before recursively calling explore on its children, then that's pre-visiting. And then once you have explored all your children, then you're post-visiting the vertex. Okay? So basically, if you replace this pre-visit call to print V, then running DFS would print out all the vertices in pre-order order. And if you replace this post-visit with print V, then running DFS is going to print them all out in post-order. Okay, let's go through an example. So this is a simple graph we have, and let's say we start running DFS, and initially everything's going to be, all the nodes are not visited, so I've colored them red for visited is false. And then we go through all the nodes, and if it's not visited, we call explore. So let's just say the first node we process is node A, so we're going to call explore node A. Okay, so then we'll set node A to be true, and then for every neighbor of A, so basically all the edge going away from A, we'll see if it's not already visited, we'll call explore on the neighbor. So we have two neighbors, B and C, so we could call explore on either one first. Typically we do it in alphabetical order when we're going through examples, just so everyone's on the same page. So I'm going to call explore first on B. Okay, so I call explore on B and then set it to true. Then I look at all of B's neighbors. That would just be C, so I call explore on that. I visit that. And now I look at C's neighbors. C has no neighbors, so we've sort of hit the base case, and we return from our recursion, and we go back to B. B also has no more neighbors, so we backtrack and go back to A. A does have the neighbor C that we initially skipped because we went to B first, But note that C is now visited. So we're not going to satisfy this if not visited case. So we also return out of here. So then we go back to this for loop here. Ooh, laser pointer. For all vertices in V, we check if they're not visited. A, B, and C have all been visited. And then we'll eventually get to D, which has not been visited. So we call explore on D. And then we'll visit D. And if you look at D's neighbors, all of its neighbors, which is C, have been visited. So we return and we're done. So hopefully that made sense. As you could see from here, we went from A to B to C, so we try to go as deep as possible, and then we sort of backtracked. So we went back to A, B, then to A to see if there's anything left, and then there wasn't. Okay, so there's also an iterative approach to writing DFS, which follows the same logic as this recursive approach that I've walked through. Personally, I find the recursive approach simpler to write out and think about, but iterative approach is just as valid. The main thing to keep in mind is we have to explicitly create a stack data structure. And this stack emulates the recursive stack that we get when we use the recursive approach. So with the recursive approach, we're repeatedly recursively calling explore. Then when we return out of that, we get this stack where we had this last in, first out structure. And if you think about it, why does this stack make sense? Well, you're always trying to go as deep as possible. So it makes sense to continue exploring the node that we just found. So the stack's last in, first out policy is perfect for this because the last node that we just found is the first node that you're going to pop out and then continue exploring. So that's exactly what we want. Yeah, so this is the pseudocode for your reference. I'm creating a stack. You add the start node to the stack, and then you iterate through the nodes in the stack as long as they're not empty. You pop an element off the stack, and then essentially now V is the element you're visiting. You set V to true because you're visiting it, and then you go through all of the neighbors of V. And if its neighbors are not already visited, so they're not already marked, then you push those neighbors to the stack so then you can visit them in future iterations of the while loop. This line here, I commented, technically might not necessary. This depends slightly on where you quote visit the node. If you visit the node here where I put the comment, then it's not necessary because even if you add nodes to the fringe that have been marked, you're not going to visit them when you because they're not going to satisfy this if condition here. But it is better to keep it because there's no need to have visited nodes on our stack because you're not going to visit them anyway. So it makes it a little bit faster to just have that check there. Okay, before we jump into BFS, let's talk about this cool application of DFS, which is called topological sort. So a topological sort is an ordering of the vertices in a graph. So it's also sometimes called a linearization of a graph. And we want to order the vertices in such a way such that if there's a directed path or a directed edge from node V to node W, then V has to come before W in our ordering. So for example, if you have the edge AD here, A has to come before D in any topological sort. And this only works for directed graphs, of course. By definition, we're talking about directed edges. And it has to be acyclic because if you have a cycle, say we had an edge from C to D, or it doesn't matter. If you had a cycle, then there's no concept of which node comes before another node in a cycle, right? So some possible topological sorts for the graph on the right would be listed here. And if just take any of them, you can look at any of the edges in the graph and see that for the first node in the edge comes first in the topological sort. But as you can see, there's multiple possible answers for a topological sort. Now, to get one possible answer, there's a pretty neat algorithm, which is straightforward. You run DFS, post order traversal. So basically, run DFS and keep track of the post order traversal of the nodes. And then you reverse this post order list. So, how does this work? Well, you will recall that post order visiting a node, you post order visit a node after exploring all of that node's children, right? So, if we reverse the post order list, a node in the list will always come before any of its children, right? Because the post order list means when you see a node in that post order list, all of the node's children will have come before, like have been processed before. So if you just reverse that list, then if you see a node, all of its children will become after it in the list. And that's exactly what we need topological sort to do. Now a common thought is, well, why can't you just do the pre-visit, like pre-order list, and then don't reverse anything, right? The problem with this is, if we do the pre-order list, we might visit a node's child before we visit its parent. And this would happen like down the path. So for example, if we start running DFS from A, maybe I go to C, and then to F, and then to H. Well, the pre-order list would be A, C, F, H, and then etc. But you can see we need D to come before F, but this pre-order list, F would come before D. So pre-order wouldn't work, whereas with post-order, we're guaranteed once we post-order visit a node that all of its children have already been processed. So that's why we take the post-order and then reverse. Okay. Oh yeah, here's a quick example for why topological sort is useful. So you might have seen this graph on I believe it's the HCAN webpage, all the CS courses at Berkeley and the prerequisites required for the course. So you can see for 61B, we needed 61A. For 186, we needed 61B and 61C. So how do we order all the courses we take such that they've always satisfied the necessary prerequisites? So say I want to take all the courses at Berkeley, and I need to take them in order such that like I've satisfied the prerequisites by the time I'm taking the course. Well, if I have this graph, you can just run a topological sort. So 61A would always come first because all these other courses at some point, or I guess you could take 70. So you could take 61A or 70 first, because they're sort of like the roots. So all other courses are pointed to by either 61A or 70. So these would have to come first in a topological ordering, and then etc., etc. So you just basically run DFS on this graph and reverse the post order. Okay, back to graph traversals. Let's talk about BFS, breadth first search. This is the yin to the yang, DFS, BFS. Same goal as DFS. We want to explore the graph, want to visit all the nodes. And like DFS, you also need to mark your visited nodes to avoid infinite runtime. But it takes a different approach than DFS. If you recall, DFS, we went as deep as possible. That's why it was called depth first. Whereas with BFS, we're going breadth first. So we're going sort of as shallow as possible. It's the opposite. With BFS, you visit all nodes one distance away from the start. Then, after visiting all of those, you visit all nodes 2 distance away. Then you visit all nodes 3 distance away, etc., etc. So here's the pseudocode on the right. And hopefully staring out at you is we're using a queue instead of a stack that we used with DFS. So why do we use a queue? Well, a queue is first in, first out, which is perfect for our case because let's go through the pseudocode for like a couple steps and it'll become clear. So we start with the start node and then you add all of its children to the fringe, right? And then because it's first in, first out, you're going to visit all of those children. So all of those nodes one distance away from the start, you're going to visit all those before you visit those children's children. So basically just changing the data structure we use drastically changes the way in which we visit the nodes. One other cool thing about BFS is we can use it to keep track of the distances the nodes are from the start node. Since we're visiting all nodes one distance away, then two distance away, etc., we can find the shortest path from the start node to another node. And then if there's multiple paths to that node, we always take the shortest path, right? Because when we're visiting all nodes one distance away, if you can get to it from the start, that's one distance away, we'll consider that. And we're not going to consider a path that takes, two edges instead, for example. And the way we do that is you just add this distance array where you set distance of s to 0 because that's your start. And then when you're going through your processing a node's children, you just set the distance of that child to the distance of the parent, like how we got there, plus 1. So for that one edge, getting from V to W. Of course, this only works because we're adding the plus 1 with graphs that have edge weights of 1 to get the shortest path. So you can also think of BFS giving us the shortest number of edges from the start node. Okay, and that leads us perfectly into Dijkstra's, which is shortest paths when we want to talk about edge weights that are different than all ones. So say we want the shortest path from A to B, BFS won't necessarily give the shortest path in terms of edge weights, it's just going to give the shortest number of edges. So here, if you want shortest path from S to T, the shortest path would take this route on the left, which is what, 80, 110. But this takes 4 edges, which BFS would give us this path, which is only its 3 edges. So we need to account for the actual distances between nodes. That's where Dijkstra's comes in. So Dijkstra's algorithm is essentially BFS, except we use a priority queue instead of a regular queue. So with BFS, remember, we're using this regular, just first in, first out queue. Now we're going to use a priority queue. And this prioritizes nodes that takes edge length into account. Like with the BFS example, we're going to have a single start node, and then we're going to try to find the shortest path from that start node to all other nodes in our graph. And it's guaranteed to produce the correct results if all edges are non-negative. So this is an important caveat. We can't have negative edge weights. Interesting exercise to see why not, and you can talk to us more about it in office hours if you're curious. And this second point we'll get more to later. It means once we dequeue a vertex, so sort of similar here, once we remove the vertex from the queue, which will become a priority queue, we've found the shortest path to that vertex. Okay. Basically, a summary of what I said, keep our priority queue guarantees that you've found the shortest path to that node once you remove it from the queue. Okay, so this is the pseudocode for Dijkstra's. Hopefully it doesn't look too crazy, but essentially we create a priority queue instead of a queue, and it's the priority values of the queue are going to be equal to the distance of the shortest path you've found to that node so far. So it's going to be a minimum priority queue then, and you're going to initially set the priority for the start node to be 0 because you're starting at the start node. So the distance to the start node is 0, and the distance to all other nodes is infinity because you haven't found a path to those nodes yet. And don't worry about edge 2 yet, really. And then it's a similar while loop structure. While the queue is not empty, you remove the smallest priority element from the queue. And this means we've found the shortest path to the vertex we removed. So key fact. And then for all the neighbors of the vertex we're visiting, here's the important part. We look at the current distance from the start node to that neighbor, and you see if the distance to the current node we're visiting plus the edge weight from that node we're visiting to the neighbor, if that if that sum is less than the current value of the distance of the neighbor, then we're going to update the distance to that smaller value. And that means that now we've found like a shorter path to W, and that path comes from V, right? We went from V to W, so we set the edge to W is from V. So that's what this line is doing. And since we updated the distance to a smaller value, we want that distance to be reflected in the priority queue. So this line here, we change, sorry, it's being covered up. You change the priority of the node W to the updated smaller distance here. Okay. Yeah, so hopefully high level this makes sense. Basically you're popping at every iteration of the algorithm, there has to be at least one vertex that you found the shortest path to so far, and then you remove that vertex from the priority queue. And so since you found the shortest path to that vertex, you look at its neighbors and see if now using that sub-shortest path, you can find a shorter path to any of its neighbors. And then you repeat that process until you found the shortest path to all the nodes in the graph. So the runtime of this is, let's think about this. We have V vertices we're processing and E edges we're processing. So the E edges we're processing comes from this for loop for all the edges. So this means that we're going to be upper bounded by processing all the edges in the graph at some point. And then this outer while loop, well, the priority queue will have all the vertices in our graph. So we're going to go through this while loop like V times, where V is the number of vertices. And then for every vertex we process, you remove the smallest. So that's going to be a priority queue operation. And for every edge, you potentially change its priority. So that's another priority queue operation. So this is going to be upper bounded by E times X plus V times X, where X is the runtime for a priority queue operation. And if you recall, using a heap implementation of a priority queue, we can get those operations down to log of the number of elements in the priority queue, and there are V elements in our priority queue, so that'd be log V. So the total runtime is E log V plus V log V. Awesome. Okay, now let's talk about this edge 2 a tiny bit more. I've bolded it here. So this distances array, after running Dijkstra's, is going to have the shortest path, the distance values of the shortest path from the start node to every other vertex. But say we want to keep track of the shortest path tree, like what are the edges that we follow in order to like retrace that shortest path? Well, that's where the edge 2 array comes in handy. So, for example, say you want to answer the question, how does the start vertex A get to vertex F for this graph, say? Well, you just call or access edge 2 of F, which says, okay, we got to F from D. So edge 2F is going to give us D. And then we can get edge 2D, and that's going to give us E. Edge 2E is going to give us C. Edge 2C is going to give us A. And now we're at the start node, and we've retraced our steps. So we know the shortest path from A to F would be A, C, E, D, F, etc. So you can use the edge 2 list to answer this question, and also ultimately like retrace the entire shortest path tree from start node to all other nodes. Okay, so now I have a demo of Dijkstra's. We're starting from vertex A. So per the pseudocode, I set the distance of A to 0, because that's our start node, and the distance of all other nodes will be infinity, right? And now I go through my while loop and I remove the smallest node. So I'm denoting that. So I'm basically in this box here, by shorthand, I'm just listing the distances of all the nodes, and I'm going to cross out nodes that I'm removing from the priority queue. And remember, the priority queue is going to be removing the node with the smallest distance value. That, of course, hasn't already been removed because it has to be in the priority queue. So here I'm going to remove A, and that means I'm going to look at all of the neighbors of A, which is B and C, and I'm going to see if I can update their distance values. So currently the distance of B and C from the previous step are infinity. So when I look at the distance to okay, so I'm looking at all edges. So that would be edges AB and edges AC. And I see the distance to B is infinity, but the distance of A plus the edge weight from A to B is 0 plus 4. So 4 is less than infinity, so I'm going to update the distance to B to equal 4. And then I'm going to update edge to B to equal A. So we got to B from A. And then I'm going to change its priority. Okay? So all that work I'm just encapsulating here is updating B's distance to be 4. And then it's the same logic with C. I update C's distance to be 2. Okay. Now I go back up the while loop, and I'm going to remove the smallest element from the priority queue. That would be element C, right? Because A has already been visited. So now the smallest element would be C. So I'm going to remove C from the priority queue. And I continue the same process. I look at all of C's neighbors. So that's going to be B, D, and E. So this is a neat example. Let's just go through B step by step, and then it's the same logic for D and E. So for the edge CB, the distance to B is from this previous step is 4, right? So distance to B is 4, but the distance to C is 2. So C is the node we're currently visiting, and the edge weight from C to B is 1. So 2 plus 1 is 3. 3 is less than 4. So we're going to update B's distance to be 3. And we're going to change its edge to be C. So now we're saying we're getting to B from C. Note this is a change because the previous iteration we said we got to B from A. Now we know we got to B from C. So you can see how Dijkstra's is like updating the shortest path it knows so far. It's only once we remove that vertex from the priority queue that we've found the shortest path. Okay, so same logic with D and E. I've updated G's source distance to 6 and E's to 7. Now the next iteration, I'm going to remove the next smallest from the priority queue, which is now B. And now I look at all of B's children. So that's D, E, and C. Note C, I technically look at C, but it's already been removed from the priority queue, so it would never get a smaller distance. So it's only really D and E that could potentially be updated. And neither of them have an updated distance, but I continue through the while loop. I remove D from the priority queue, and then lastly, I remove E. So the priority queue is now empty. I am done. And this is these are all the finalized distances, and this is the shortest path tree that we would get if we retrace the edge to array that we've kept track of. Okay, I hope that Dijkstra walkthrough made sense. Okay, let's talk minimum spanning trees. So, what is a minimum spanning tree, or MST? Well, let's break this down. First, it's a tree, so that's an acyclic connected graph. And if you have n nodes, that means you have to have exactly n minus 1 edges. And a tree can be as small as a single node in the graph. A spanning tree is a tree that spans or includes all nodes in the graph. And then a minimum spanning tree is a spanning tree with the minimum total edge weight. Now, there could be multiple minimum spanning trees for a graph if there are multiple spanning trees with an equal minimum total edge weight. Okay, so before we go into like Kruskal's and Prim's, an important piece of theory to be aware of is the cut property. So this is the basis of the proof for why Prim's and Kruskal's work for constructing minimum spanning trees. First, what's a cut? So a cut is an assignment of a graph's vertices into two non-empty sets. So it's basically like some of the vertices are one set, the rest of the vertices are another set. That is a cut, and you can think about it like you're cutting the graph into like two parts. A crossing edge is an edge which connects a vertex from one set to a vertex from another set. So the edge is crossing from one set to another set. And then the cut property is the fact that given any cut of a graph, the minimum weight crossing edge is in the MST. So that's a pretty powerful statement. It's saying if you come up with any cut, so like we have a graph, this edge could be, this node could be in one set, and all the other vertices could be another set. We look at all the edges across that cut. The minimum edge across the cut is in the MST. Or in this case, all the gray nodes are in one set, all the white nodes are another set. This thick line is the minimum weight crossing edge, and we're saying that minimum weight crossing edge across this specific cut is in the MST. Okay, so why is this the case? It's a little bit of a proof by contradiction. So suppose we have some MSTT. And the proof is kind of out of scope. Like, you're not going to be expected to explain. It's good to know. We're not really going to be testing you on proving theory and stuff like that. But it could be helpful for true-false questions. So suppose we have some MSTT, and assume the minimum edge crossing the cut is E. And we're going to say it's not in T, okay? So we're sort of approaching this from a contradiction standpoint. Okay, so add that edge, add that minimum crossing edge to T. And since we said T was already a minimum spanning tree, this would create a cycle, right? Because a tree has to have exactly n minus 1 edges. We just added an edge. This cycle must have another edge, E prime, across the cut. Right, so now we have two edges across the cut that created our cycle. If we remove the edge E prime that already existed in T, then we are left with a spanning tree with total weight less than or equal to the original weight of T. Why less than or equal? Well, we said E is a minimum edge across the cut. So if we removed another edge across the cut, E prime, and we added E as well, then the total weight is going to be at most equal to the weight of T if E prime had equal value to E. So basically then this new spanning tree that we created must be also a minimum spanning tree. Yeah, so that's the crux of the argument. If you were to add the minimum edge, it'd create a cycle, and then you could remove the larger edge in the cycle. So the smallest edge must be in the MST. There's no reason it would not be in the MST, because then you can make the MST have a smaller total edge weight by including it instead. Okay, I know that's a little bit confusing. Hopefully the intuition sort of makes sense. The intuition is the main thing to take away from it, not the nuances of exactly how the proof is outlined. Okay, so Kruskal's algorithm is one approach to construct a minimum spanning tree given a graph. So we order the edges from smallest to largest, and then you add edges into the minimum spanning tree in order from the list that you create, and you skip edges that would cause a cycle. So basically, if you here it's in the pseudocode. So when we're considering adding an edge that you from the sorted list, if U and V, the endpoints of the edges, are already connected, so they're already like a connected component, then you don't add that edge. So this is where we are going to use like the union find operations that we've learned about for Kruskal's. The runtime of this is going to be E log E for sorting the edges. And then we're going to have E find and E like union operations, each of which take essentially constant time. So the runtime is upper bounded by E log E. And let me edit this. It says E log E. We want E log. Okay. Okay. Quick detour into union find because we are using this in Kruskal's. So it's a data structure where we keep track of elements in sets, and we can check whether two elements are in the same set or not. And the reason why it's useful is basically we're adding all our vertices to sets. Once we like add the edge to the MST, you union together the two vertices so that in the future you check if the two vertices are part of the same connected component. If they are, then you don't want to add that edge because you'd just be creating a cycle. So we have this find operation which finds the set it's part of, and this union operation which connects the vertices, or connects two elements to be part of the same set. So what it does is we achieve this by storing the elements in trees, and when we union together two sets, you make the root of the smaller tree point to the root of the larger tree. So say we're connecting D and F. Then you'd find the root of D, which is A, you'd find the root of F, which is E, and you connect E to A because E's tree is smaller. So yes, the resulting union will look like this. And then fun fact, path compression is every time you call find, like for example, we have to find the root. So you started from D and you looked at the parent of D and the parent of C, etc. An optimization is to connect all the nodes you traverse to the root. So when you're calling find on D, you see D, you see C, you can connect D to A right away, so it just makes future find operations faster. The next time you call find on D, you immediately know the parent is A, you don't have to go through C. So with enough find operations, you can get like a tree structure that is super flat. Like almost all the nodes would be pointing directly to a root, and this means that our union find operations will be almost constant. So that's why for this, when we're analyzing the runtime, yes, we have E find and E union operations, but that's like the runtime overall, it's going to be dominated by E log E because we can assume that the runtime of these union operations is going to be less than log E. Yeah, so this is a TLDR. Treat those operations as almost constant. Okay, so that was Kruskal's. Now we're going to go into Prim's algorithm, which is another approach for constructing minimum spanning trees. The cool thing about Prim's is it's essentially exactly the same as Dijkstra's. So if you understand Dijkstra's, you'll understand Prim's. The only difference is with Dijkstra's, we kept track of the distances, the total minimum distance from the start node. Whereas with Prim's, we're going to keep track of just the minimum edge weight. So what does that mean? It means here, so I just renamed the dist array to cost array, but it doesn't really matter. Instead of doing like the distance to U plus the weight from U to V, we're just going to consider the weight of U to V because we only care about like the minimum edge weights. We don't care about like the distance like getting to one of the endpoints of the edge. And then some points, it's the same runtime as the Dijkstra's because we still have a priority queue. We have V times we remove something from the priority queue and up to E times of decreasing the priority of an element in the priority queue, so that's E log V plus V log V. And then Dijkstra's needed a start node, so for this, we're just going to start at any arbitrary node. It doesn't matter. So just pick any start node and give it a cost of 0. And then here in red is the main crux of the new algorithm. At each step, we add the shortest edge, connecting a node in the tree to a node not in the tree. And by the tree, we mean the minimum spanning tree we're constructing. So you can think prims, you start with a tree which is just the start node. That's a quote-unquote tree with one element. And then you look at all the neighbors of that start node, and you're going to add the neighbor that has the smallest edge from the start node to the neighbor. So now your tree has 2 nodes. And now you're going to look at all of like those 2 nodes, all of their neighbors. You're going to choose the next minimum edge, etc., etc. So this satisfies the cut property because we have 2 sets, basically all the nodes in the tree that we've constructed so far, and then all nodes outside of the tree. And every iteration, we're adding the minimum edge across this set. Or when we delete the min, we're like, this U is becoming part of our MST, and this is the minimum edge across the set. Also, I think I skipped from Kruskal's. Yeah, so Kruskal's is also satisfying this cut property. Since we're always choosing the minimum edge, then naturally we're always going to be choosing a minimum edge across some cut if we're choosing a minimum edge overall. So both prims and Kruskal's satisfy the cut property, and that's why we end up creating an MST. They're just different approaches. Okay. That's it for the review. Now I'm going to move on to the worksheet. And the first questions are about MSTs, so that's perfect. Okay, so we're given the above graph, and it asks us to list the edges in the order they're added to the minimum spanning tree by Kruskal's and Prim's algorithm. And assume Prim's algorithm starts at vertex A because we have to pick some arbitrary vertex for prims. And assume ties are broken in alphabetical order. And this is just for convenience, so that like everyone's answer looks the same. And then denote each edge as a pair of vertices, so A, B is the edge from A to B. Okay, awesome. Let's go through this. So we're going to start with prims, and I've put up the pseudocode for your reference again. So we're going to start at A. So the cost of A is going to be 0, and we're going to add that to the priority queue. All the nodes are going to be added to the priority queue with cost infinity, and then A is going to be added with cost of 0. So initially, we're going to delete A from the priority queue because it has a minimum cost, and then we're going to look at all the neighbors of A. And we're going to look whether the weight from A to its neighbors is less than the cost of the neighbor. And for sure, the cost of everything right now is infinity, so we're going to update the cost of B to be 6, the cost of C to be 12, and then that's it, because that's all our neighbors. So then for the next step, we go back to our fringe and we want to delete the minimum. Well, the next minimum thing from the fringe would just be this B, because it has a cost of 6 versus C is 12. Okay, so we take B off the fringe, and now this is basically the minimum spanning tree that we've constructed so far. 2 nodes, A connected to B. And I can continue through this process. So C has a cost of 12 from before, but now I'm going to look at the neighbors of B. So G is going to have a cost of 4, F is going to have a cost of 7, E is going to have a cost of 4. And then C, we're going to update its cost to be 3. Although, essentially, the only thing you need to really keep in mind with prims is this last bullet point here, which is at each step, add the shortest edge, connecting a node in the tree to a node not in the tree. So we can just think about, okay, this is the tree we have so far. Don't even worry about the pseudocode for prims. You can just look at all the edges coming out of this tree. So that's these edges. We have A to C, B to C, B to G, B to F, and B to E. And we look for the minimum edge coming out. And that would be B to C, right? That has an edge weight of 3. So then I'm going to add that next to the tree. Okay, so now the minimum, we can look at all the edges coming from this tree, which is now C to D, C to E, B to E, B to F, B to G. We're not going to consider A to C because that would create a cycle, so we disregard that. And okay, now we see it could be either B to G or B to E. Both of them have value of 4. Since it says assume ties are broken in alphabetical order, E comes before G, so I'm going to add B to E. Awesome. Okay, so then for the next iteration, I look at all, again, the smallest edges coming from the tree we've constructed so far. So that would be E to F now, because this has a value of 2. Okay, and then all the edges coming from the tree are now B, G, and C, D, for the edges that aren't just connecting us to ourselves. So the next smallest would be B to G, and then lastly C to D. Awesome. So this is the ordering that we went through: A, B, B, C, B, E, E, F, B, G, C, D. Perfect. Okay, now let's go through coruscles. So coruscles, this is the pseudocode. We sort the edges by weight, and then we go through those edges in sorted order. And basically, we just add those edges to the MST, as long as adding that edge doesn't connect us, doesn't create a cycle. So basically, they're not already part of the same connected component. So we add EF because that's the smallest edge. Next smallest would be BC. Next smallest would be BE or BG, alphabetical order, so we're going to do BE. And then the next smallest now is BG. Now we're looking at 5, that'd be the next smallest, but if we call find of C and find of E, they're part of the same connecting component. See, they're already part of the MST, so we're not going to connect them, right? And connecting them would create a cycle. This if case is going to fail. So we skip the 5. So the next smallest would be this, right? A to B with a value of 6. And then next smallest would be 7. This would just connect to ourselves. So we're going to skip that. And then it'd be the 9, C to D. And for a good measure, we're going to go through the for loop for all our edges. A to C has a value of 12, and it's going to just connect it to ourselves, so then we skip it. Okay, so then we're done, and this is the order in which we process the elements. Okay, now there's just like some general true-false and conceptual questions. Is there any vertex for which the shortest path tree from that vertex is the same as your prim MST? So basically it's asking whether, so how do we get the shortest path tree? We can run Dijkstra's. So is the tree we get with Dijkstra's the same as the tree we get with prims for starting at a given vertex? So let's look at the tree we got with prims. So this is a tree we got with prims, and if we look at it, we started at vertex A with prims. It does seem to be the shortest path tree, and if you check everything, it ends up being the shortest path tree. So like shortest path to B is definitely 6. To G, that would be this path. To D, we're going to skip the 12 and go to B, C, D. Yeah, so in fact, this answer is yes, because for vertex A, which we did, and also for B and G, it would be the same tree. It was sort of lucky that the example we did starting at A happened to have the same tree. In general, if you're trying this out, start from a vertex around the middle of the graph. That has a decent likelihood of having the same shortest path and MST, because you're sort of, if you start around the middle of the graph, all the nodes are likely to be close to you, so you're less likely to take maybe convoluted paths for which the MST would not match the shortest path. Okay, moving on to C. True false, adding 1 to the smallest edge of a graph with unique edge weights, so that's a key point, unique edge weights, must change the total weight of its MST. So this is going to be true. The reason being is there's two cases where the smallest edge is still part of the MST. And in this case, the MST's total value will increase by 1. Or the smallest edge is now no longer included because adding 1 was too much, but then some larger edge would take its place. Of course, this is for if we have unique edge weights. If you didn't have unique edge weights, then you could have multiple edges with the same smallest value, and it's possible the total weight would not increase. Okay, true, false, the shortest path from A to B in a graph is the same as the shortest path from A to B, using only edges in T, where T is the MST. So it's saying like, this is sort of similar to saying like, is a shortest path tree the same as the MST tree? Clearly not, and you can come up with some counterexamples pretty quickly. So with the given graph, consider edges C and E. This 5 was not part of the MST, but it would be the shortest path from C to E, just taking this 5. If you weren't given a graph, then I always say, like, just draw the simplest counterexample you can think of for these like true-false problems. Because this question is phrased in a way like the shortest path from A to B is like always the same. So with this always the same, you just need to come up with some small counterexample and then to answer false. So here, if I have like 3 nodes with edge weights 2, 1, and 2.5, the MST would take this 2 and this 1. But then the shortest path from this node to this node would take the 2.5, so it wouldn't go along the MST. Okay? True, false, given any cut, the maximum weight crossing edge is in the maximum spanning tree. So you can imagine creating an MST, but instead of minimum total edge weight, you want maximum total edge weight. And in this case, it's going to be true. It's the same logic as the cut property that I've talked about earlier. You just replace smallest with largest in your proof. So this, I'm not going to go through this all again, but this was the cut property. And for the proof, you can think about it, okay, if you're trying to find the maximum spanning tree, you'd add the maximum edge across the cut, and this exact logic applies, you just replace minimum with maximum, and yeah, logic follows closely. Okay, more true-false questions, my favorite. Let's start from the top. If a graph with n vertices has n-1 edges, it must be a tree. So this is tricky because we know a tree, like a graph with n vertices that is connected and has n-1 edges, it's a tree. So this is false because it doesn't specify that the graph was connected. So we could have sort of a disjoint graph with n-1 edges, in which case it would not be a tree. The adjacency matrix representation is typically better than the adjacency list representation when the graph is connected, or very connected, sorry. So to be honest, I think on an exam this typically better is slightly ambiguous because it doesn't really specify what better means. But from the context, we just have to take that to mean, okay, what are the runtime space complexity of operations when you're using an adjacency matrix versus an adjacency list? And if you think about it, if the graph is super connected, what this means is between any 2 nodes, we likely have an edge. So in this case, then adjacency matrix can in fact be better because typically it's worse because if you think about it, space is v squared. Scanning at vertex's neighbors is v, etc. However, if the graph is super connected, the adjacency matrix representation will also be roughly v squared because we'll have roughly v squared number of edges. Note the maximum number of edges in a graph we can have is v squared. And if it's very connected, then we'd have close to v squared edges. And again, like iterating through our neighbors is also going to be like iterating through a list of size roughly v. But then the one advantage adjacency matrix has in this case over an adjacency list is the has edge operation. So this would be checking if vertex A has an edge with a specific other vertex X. So this we can do in constant time with an adjacency matrix. We just go to that spot in the matrix, AX. Whereas with an adjacency list, you have to loop through that list and see if vertex X exists in the list that A is pointing to, which could be potentially big O E time if the graph is very connected. Moving on. Every edge is looked at exactly twice in every run of DFS on a connected undirected graph. So the key thing to keep in mind here is that the graph is undirected, so that means this is going to be true. The reason being is you can think of a undirected edge as a directed edge with an edge like an arrow going in both directions. So when we run DFS, it's going to consider both of those directions, right? If we have, maybe makes it's easier if I draw it out. If we have something like this, let's go full screen. So if we're looking at, so this would essentially be what an undirected edge is treated like in a run with DFS, because we can go in either direction. So DFS is going to consider the edge going like left to right, and then it's also going to consider going right to left. So yeah, every edge is going to be looked at twice because essentially an undirected edge is basically two edges represented as one. Okay. D. In BFS, let D of V be the minimum number of edges between a vertex V and the start vertex. For any two vertices U, V in the fringe, the difference between D of U and D of V is always less than 2. So this is also going to be true. The reason being is unique to what BFS is doing. So with BFS, we always try to find all nodes one distance away from the fringe, or from the start vertex. Then we find all vertices 2 distances away, 3 distances away, etc. So that means our fringe is going to contain values that are all 1 distance away. And then it also might contain some values that are 2 distances away. But we're going to then process all the 1 distance away values before we visit the 2 distance away values. So there's no way we could have 1 distance away values and then also 3 distance away values, because that would mean we'd have to process 2 distance away values to get those 3 distance away values. But to do that, would have to have finished processing all the 1 distance away values. So at that point, again, the difference between the distances of 2 vertices in the fringe would be less than 2. I realize that's a lot of talking, that a lot of visuals, so I understand that didn't make complete sense. I've drawn out this little diagram, which hopefully makes more sense. So this is a tree, which is a graph, and this generalizes to more complex graphs as well. So I start with a Q, the starting vertex is 1, and then I pop that 1 off the Q, and I'm looking at all the children of 1, so that'd be 2, 3, 4, so now my Q is 2, 3, 4, right? So all my values on the Q are the same distance away from the start vertex, so the distance is, in fact, the difference between the distance between any 2 vertices in the fringe is 0. Then I go and process 2, and I look at 2's children. So that would be 5 and 6, and I add that to the end of the queue. So I have on this queue nodes that are 1 distance away from the start vertex, that'd be 3 and 4, and nodes that are 2 distances away, 5 and 6. Now, the only way to get nodes that are 3 distance away from the start vertex onto the queue, so that would be vertices like 9 and 10. The only way to get 9 and 10 on the queue is if I process 5, which is 2 distance away. But I can't process 5 until I process all the nodes that are 1 distances away. So there's no way I'm ever going to get 2 nodes on my queue that are like more than 2 steps apart from each other in levels from the start node. So in this case, the 3, 4, and the 5, 6 are just 1 level apart from each other. There's no way it can get like 3 levels apart from each other. So this is going to be true. The difference between those distances is always going to be 0, or it's going to be 1 in this case. Okay. Yeah, this is what I said. Distance is going to be the same level, so 0 or 1 level apart. E, given a fully connected directed graph, a directed edge exists between every pair of vertices, a topological sort can never exist. So fully connected means, yeah, we have an edge between every pair of vertices. The key thing to note is, can we come up with a counterexample? Okay, let's look at the language. A topological sort can never exist for a fully connected graph. So to make this false, we just need to come up with one example of a fully connected graph where some topological sort does exist. And the simplest example is just the one I drew here. We have 2 vertices, 1 edge, 1 directed edge, and it's fully connected. You know, every vertex has an edge between them, and you can certainly come up with a topological sort. This node would come before this node in the topological sort. And the given solutions come up with a more general example, which you just have a chain of these. So basically, any linked list you can create a topological sort out of, and it would be fully. Or, sorry, not any linked list. A linked list of size 2 that I've drawn. And this is a more general case where you have for all vertices where I is less than j, you draw a directed edge from I to j, and then you just enumerate the vertices, like 1, 2, 3, etc. Okay, but like in my opinion, just coming up with this simplest counterexample is like the easiest way to go about this. If anything, for true-false questions that are true, it's a little bit trickier because you need to like do some logic and convincing yourself this is true. Whereas with false, oftentimes you can come up with some quick counterexample and then you know for sure it's false. Okay, question 3. In some graph G, we are given a sorted list of nodes sorted by their distance from some start vertex A. Design an algorithm to find the shortest path tree starting from A in the linear O of V plus E time. Okay, so with this question, we're not given the shortest path distances from the start node, but we're given the nodes sorted by their shortest path distances. So this probably is going to come in useful because that extra information is going to allow us to modify Dijkstra's to give us a linear runtime rather than a log linear runtime. So the runtime is a hint in a way because we know that the Dijkstra's runtime is E times X plus V times X, where X is the runtime of priority queue operations. So if the goal runtime is just E plus V, it suggests that we've gotten rid of priority queue operations. Okay, so why do we have a priority queue in the first place? That's the answer. I guess I'll just go into the answer. Okay, so ignore this wall of text for now. This is the pseudocode for, and ignore the crossed out stuff. So this is the pseudocode for Dijkstra, right? So we have this priority queue, which to keep track of the shortest path distances that we've found so far, and at every step in the algorithm, we remove the node to which we've found the shortest path to. So when we remove the node, it means we've found the shortest path to that node, and this is the next closest node to the start that hasn't been visited yet, right? And then the next iteration, you remove the next shortest path node. But if you're already given the list of sorted nodes to start with, then we actually don't need the priority queue because we know the order that the nodes will be removed from the priority queue if we were to have it. So we know that information ahead of time. So instead, we could just iterate through the nodes from the sorted list as if we pop them from some imaginary priority queue, right? So instead of this like while priority queue is not empty, remove the smallest, you just go through the sorted list, right? Because you know that sorted list is going to be like the order in which you've removed the smallest elements from the party queue. So long story short, you run Dijkstra's, but you don't keep track of a party queue. You just go through the sorted list of nodes, and then you still update the distance values and the edge 2 values. So you end up with the edge 2 getting a shortest path tree. So since we don't have this remove smallest or change priority operations, the runtime is just E for this for loop, and then V for iterating through all the edges in the list. So it's E plus V. Awesome. Okay, so this one is like, so this is like a classic design problem that you might encounter on an exam. The key is to start from a place that you already know. So you already know Dijkstra's. Typically, we're not going to ask you to come up with something like completely out of the blue. Oftentimes, it's going to be either modify an existing algorithm, like Dijkstra's in this case, or like use an existing algorithm in creative ways. So that's what this next question approaches. So this question, we modified an algorithm. In this question, the way we're going to design it is we're going to use an algorithm that we already know to sort of create a new algorithm. So for the scenarios, write a description of an algorithm for finding the minimum spanning tree for an undirected connected graph, naturally. Okay, so part A is supposing if all edges have edge weight 1. The hint is the runtime is O of V plus E. Okay, so again, we can't be like sorting edges because that would be E log E. Prim's algorithm is V log V plus E log V. So you might think, okay, it could be Prim's, and then you just get rid of priority queue operations. But let's think about this like edge weight 1 thing. So if all of the edges have an edge weight of 1, and we know all trees will have n minus 1 edges, so all spanning trees have the same number of edges. And regardless, all the spanning trees will have then edge weights n minus 1 edges of weight 1. Long story short, all the spanning trees will have the same total weight, right? So basically, all we need to do is construct a tree that connects all the nodes. So we can just run a graph traversal algorithm like DFS or BFS and keep track of the tree that we've traversed. Yes, you could also like try to modify Kruskal's and skip sorting edges. So you skip the E log E step, but then we'd still have to do those union find operations to prevent creating cycles, and that would take a bit more than constant time, technically, so it wouldn't be V plus E. Okay, part B is extend this a little bit further. Say all edges have edge weight 1 or 2. In this case, it's basically doing what we did in part A, but extending it a bit further so we can isolate all the edges with weight 1 and then isolate all the edges with weight 2. So we do it in sort of 2 parts. So the first part is you remove all weight 2 edges from the graph, so only weight 1 edges remain, and then you run your algorithm from part A. And then side note that when we run DFS in this case, the graph is likely unconnected, so the result is going to be sort of like a DFS forest, right? So you have a tree, but you may have multiple trees because the graph without weight 2 edges will be disconnected. So these multiple trees produce a number of connected components, which you'll treat an entire connected component as a node in a new graph G star. And then I'll skip this point for now. You'll look at all the weight 2 edges in the original graph, and for each edge, if the nodes containing the 2 endpoints are not already connected in G star, then you add that weight 2 edge between the 2 nodes. And then finally, you just run the algorithm from part A to come up with some like DFS tree for the entire MST, and then you're done. So I want to mention this point here, which is decomposing your graph into like sub pieces that then you treat as nodes in a new larger graph is kind of it seems out of the blue now, and like I think designing this from without having seen something like that before would be incredibly difficult. But now it is a common problem solving technique. So I would like the specifics for this algorithm is maybe not so relevant, but like that point is something I would take away. So to repeat is like for this part of the algorithm, we've removed some edges from the graph, and then we've run like a DFS forest, and removing edges basically gave us a number of components that may be disconnected. So we have a number of like connected components that are disjoint from another, and then you treat an entire connected component as a node. So now you have a new graph with nodes, and then in the like second part of the algorithm, in your new graph you choose to like connect those new nodes in some way, and then you run another algorithm on top of that, and then you combine the two sets of edges from these two parts into a resulting like tree in this case. Okay, so that's actually it for the worksheet. Hopefully that made some sense. Feel free to ask questions on Piazza if you have any, and I will see you next time.